Okay, let us solve the air standard diesel cycle problem. Let's first see what are given. It's a great idea always to draw the TS diagram even before reading the entire problem. So we have a constant pressure line, which is less steeper than a constant volume line. Okay, let's see now what are known. As you can see, state 1 is completely given to us. The compression ratio is, well, the maximum temperature is given. Yes, the compression ratio is given. And now we can answer any kind of question, mean effective pressure or thermal efficiency or cutoff ratio. Let's find everything about this cycle. So we'll go, as usual, find out all the states and then analyze each process, especially the heat addition and heat rejection process, which will lead us to all our answers. So state 1, pressure is given, temperature in Kelvin is 293 Kelvin. So we can very quickly find the specific volume to be P by RT using the ideal gas equation. And we'll just assume, because the mass is not given in this problem, the mass is 1 kg. So all our analysis is based on a mass of 1 kilogram. And this is our specific volume. Before we proceed, let's make sure we can verify the answer. I already launched the test calc using the PG model, the reciprocating cycle. So 95 kPa, mass equals 1 kg, and temperature is 293 Kelvin. That gives us a specific volume is 0.885. That's pretty close. Okay, from 1 to 2, entropy remains constant, so we can use isentropic equation. So state 2 is, we know mass is the same and entropy is the same. Therefore, T2 over T1 equals V1 over V2 to the K minus 1, or V1 over V2. Because mass doesn't change, we can interchange capital V and small v. And V1 over V2 is the compression ratio, volumetric compression ratio, which is 20, and K is 1.4. So therefore, T2 is T1, which is 293 times 20 to the 0.4, and that gives us 972 Kelvin. Of course, the specific volume is already given to us. Specific volume is V1 over 20, 20th of the original volume, and V1 being 0.886, so specific volume is about 0.044. Okay, so we found the volume, specific volume. We know the temperature now, and to find the pressure, we can always use PV equals RT. Temperature is known, 972. The specific volume we just found, 0.44, and that gives us a pressure of 6303 kPa, large pressure. Let's go and verify. So we go to state 2. Mass is the same. Volume is VOL divided by volume 1 divided by 20. Notice mass and volume will give us specific volume, so we could write specific volume to be 1/20th. Obviously, we cannot enter specific volume now. Even if you click, you'll find an error message, which is not shown here at the bottom because our screen is kind of limited. And entropy, S2 equals S1. So that gives us the temperature state 2. That's kind of correct. So state 1 and 2 have been found. State 3. State 3, the information supplied to us, we know for sure P3 is equal P2, and we just calculated pressure 6303 kPa, and the temperature I believe is supplied, if you recall, 2000 degrees Celsius, which is 2273 Kelvin. So pressure and temperature, there's therefore specific volume we can find. Specific volume will be PV equals RT. Using that, R and that gives us V3 or V at state 3 to be 0.103. Suppose one of the question is find the cutoff ratio. So what is the cutoff ratio? Recall, cutoff ratio is simply the volume at the end of heat addition after the fuel is sprayed from the initial volume, which is V2. Initial meaning after the isentropic compression, the volume is V2. That's when the fueling starts. V3 is when the fueling ends, heat addition ends. So V3 is 0.103. So, and V2 is 0.044, and that gives us a cutoff ratio of 2.34. So RC equals 2.34. To verify that, we go back to the test calc and state 3. What we know is that pressure doesn't change. It's constant pressure heat addition. P3 equals P2. Of course, mass is the same. And the temperature was supplied to us, 2273 Kelvin. So that gives us V3. And to find the cutoff ratio, we can go to the I/O panel and figure that out. V3 divided by V2, which is 2.336, quite close to what we just calculated. Now to find state 4, which is isentropic to state 3, notice that we can use the isentropic relationship again, but this time it's a little bit complicated for the diesel cycle because one of the line is constant pressure and the line is constant volume in this diagram. Of course, this is the TS diagram. So to find, we know that T3 over T4 isentropic relationship, you recall from equation 11 in your table J handout, T3 over T4 will be V4 over V3 to the K minus 1. Again, this is equation 11, table J. This is the same equation we used when we found T2. So to find T4, we know T3, V4 over V3. Notice V4 is same as V1 because constant volume line. But V3 is not equal V2. So if we introduce a V2 here, it will be V2 over V3 to the K minus 1. And we notice that V1 over V2 is this ratio of volume is our compression ratio R. And what is V3 over V2? That's what is the cutoff ratio. So it's 1 over RC to the 0.4. K is 1.4 minus 1 is 0.4. So therefore, T4 is T3 divided by R over RC. R is 20. Okay, this is 20 divided by 2.34 to the 0.4. And if we calculate that, it is 8.547 to the 0.4. So we know T3 2273. So therefore T4 can be obtained as 963 Kelvin. Of course, using the test calc, it's rather much easier to calculate state 4 because we know entropy at 4 equals entropy at 3, isentropic to state 3. Mass doesn't change. And we know the volume at state 4 is equals the volume at state 1. That's geometrically limited, right? The cycle must end at the same place. And that gives us 962, which is pretty close to the temperature we got. One good thing to do here is to draw a TS diagram to make sure we didn't make a mistake. 1, 2, 3, 4 is our cycle. We know if we draw a constant pressure line through state 2, we select state 2, line for state 2, constant pressure line, click on P equals C, it must go to 2, 3. And if we draw a constant volume line through state 1, so we select state 1, and we draw a constant volume line, they must pass through 1 and 4. And of course, if we draw isentropic lines, are obvious, vertical lines, so we see that, you know, we get back what we thought, what we assume, what we presume the Diesel cycle to be. So all the states have been calculated. Now let's go and figure out the heat transfer. Especially we are interested in heat added in the constant pressure process and heat rejected. Because Q in and Q out, if we subtract the two, we'll get the Q net. And that's going to, Q net is equal W net, so we can find all the answers that we are looking for. So Q in is M times H3 minus H2. Again, recall where it comes from. Delta U equals Q, we all know the energy equation for a closed process. But for a constant pressure process, we can show that, you know, this equation simplifies to be such that delta H equal Q. And from there we get this formula. So substituting M Cp T3 minus T2, or we can call it small q, which is Q in over mass. Per unit mass, the heat added is Cp times T3 minus T2. Cp is about this, and if we substitute the values of T3 and T2, we end up in 2273, 972, and that's equals 1304. Similarly, Q out can be calculated as M H4 minus H, sorry, not H, it will be U4 minus U1, right? Because volume remained constant during the heat rejection process. There is no M, I'm sorry, I divided by M already. So it's CV times T4 minus T1, and CV is 0.718. T4 is 963 and T1 is 293, and that gives us about 479 kilojoule. Let's go and verify these numbers. So we go to the process panel. Process A is our compression process, state 1 to state 2. Calculate. So notice we can find the boundary work done during compression here. It's negative. Heat is added. Work is added. Process B is the heat addition we are after, 2 to 3. Remember that you have to calculate all the processes so that the cycle panel will work. Even though we only need heat in and heat out for our manual calculation, for the test solution, we need all the processes. So process A, B. Process C is what? Again, it's the power stroke from 3 to 4. Click calculate, and we found the boundary work. And finally, the final process is heat rejection from 4 to state 1. We calculate, we find the heat transfer. So all the energetics had been calculated for each processes. Q is 479 for heat rejection, which is pretty close. This is a positive number because, by the way, the answer will be so many per kg here. I'm sorry, kilojoule per kg, because this is small q is per unit mass. So this answer is pretty close to what we got through test calc, and this is also for process B. The answer was 1304 was the heat transfer, and yes, we got about 1304. So now that we know Q in and Q out, so W net, small w net equals capital W net by M equals QW net by M, which is Q net is known, is Q in minus Q out, which if you substitute, you can show it's about 825 kilojoule per kg. So therefore, thermal efficiency, which is W net by Q in, which is small W net over Q in, and that is 825 is my W net, and Q in we already calculated to be 1304, which is about 63%. We can go to the cycle panel. Because we have calculated all the processes that complete the cycle, all we need is to click a calculate button, and the thermal efficiency is shown to be 63.3%. If we want to find other quantities such as what is MEP, essentially mean effective pressure is an average pressure that produces the same amount of output as the piston moves from top dead center to bottom dead center. So the change, the displacement times pressure. So essentially W net divided by V1 minus V2, or capital W net, this is the same thing as V1 minus V2. Essentially we're taking the mass out. We found W net to be 825, and the volume changes are 0.886 minus 0.044, and that produces 980 kilopascal. You can show that the unit kilojoule per kg here, and meter cube, when you manipulate, it will produce kilopascals. So there you have it. We found all the answers we need to find. If we go here and do a super calculate, the entire output, a detailed output of the entire solution is produced in this panel. And part of it is the test code. If you just copy and paste the test code in your favorite word processor, save it for future use, you can always come back and paste it in this I/O panel. Click the load button, and voila, you can regenerate the solution. You can also do a bunch of parametric studies. Suppose you change a parameter and click the super calculate button, you can see how it impacts the efficiency or the network output, etc. So I'll stop here and let you pursue whatever what if scenario your mind can envision.